When we chat with our friends using instant messaging apps, our messages are encrypted, which requires a public key or a shared secret to make sure that a hacker cannot crack our chat history. The most common method to establish a shared secret without explicitly sharing the secret is Diffie-Hellman key exchange.
To see how it works, we need to first have an idea of modular arithmetic. The expression here, a is congruent to b mod m, means that a minus b divided by m is an integer. Usually, b is the remainder when a is divided by m. The important thing here is that modular arithmetic is irreversible. Okay, now let's look at Diffie-Hellman key exchange. Let's say Alice and Bob are sending messages to each other. To establish a shared secret, we first have a prime generator g and a prime modulus p. Alice and Bob have their own private keys a and b, which are random numbers. Next, Alice will use gp and her private key to calculate her public key, which is g raised to the 8th power mod p. Bob will also calculate his public key. Alice and Bob then send their public keys to each other. Because modular arithmetic is irreversible, even if the hacker knows the public keys, there's no smart way to get the private keys. Now, Alice will use Bob's public key to calculate the shared secret, which is Bob's public key raised to the 8th power mod p, and Bob will do the same. The result is shared because it is equivalent to g raised to the power of a times b mod p. You can see this with real number examples.
So let's use clay and colors as an analogy to illustrate the process of Diffie-Hellman key exchange. The private keys of Alice and Bob are represented by a red ball and a blue ball respectively, and the generator as well as the prime modulus will be represented by this green ball.
Alice and Bob will use their private keys and the values represented by the green ball to calculate their public keys, which are represented by the purple and cyan ball. They will then use each other's public key to calculate their shared secret, which is this indigo ball. Technically, it is possible to enumerate all colors to find Alice's and Bob's private keys, and it is also possible to enumerate all numbers to find the shared secret. But in reality, the private keys and the prime modulus p will be hundreds of digits, so it will be computationally impossible to crack the code.